Consider this before viewing patterns, symmetry, and beauty. It's no coincidence that people find familiar shapes and patterns appealing. Our minds easily recall simple geometric forms, such as the circular shape of the moon or the triangle that frames a tree. As you watch, note examples of how simple mathematical relationships play a role in what appears beautiful. Assignment Discovery now presents Patterns, Symmetry, and Beauty.
When we look at an object or hear a sound, we cannot escape the imprint of personal experience. Each person's definition of beauty defines who they are.
Beauty is truth.
Beauty is inspiration.
Beauty is the Berlin Wall coming down.
Beauty is a double hot fudge caramel swirl sundae.
Beauty is in the eyes of the beholder.
But if beauty were only in the eye of the beholder, we'd never agree. Yet, sometimes we do. There are some things that appear beautiful to most of us most of the time. That's where science comes in, trying to understand why we like what we like. It turns out there is a structure to the world, a system of shapes and patterns and sounds that triggers pleasure in us. You probably don't look at the beauty of nature and see equations. You don't see a circle whose circumference is equal to pi times twice the radius. You see the moon. But science has found that the elegance of mathematics often underlies the beauty of nature.
Mathematics is really the loom upon which God weaves the fabric of the universe. We are like a traveler in a jungle, or someone searching for gold in a gold mine. We're finding things that actually exist out there. And I believe mathematics can be used to describe much of the world we live in.
The easiest mathematics to see is geometry, the study of points and planes, angles and solids.
Looking great. Okay.
Galen Rowell is a wilderness photographer who searches out structure in nature's diversity. He finds a geometry of life.
I think that our minds search out geometric forms that we clearly recognize. Triangles and circles and squares, all sorts of things that are relevant to our lives. We look to those things and we want them to be simple and clean. We don't want them to be all jumbled. And we remember very simple forms.
So the pattern recognition circuits in our brains tell us we're seeing triangular trees and circular moons. And that's true no matter how closely we look. Even through a microscope, we see a world of floating geometries. From microbes to man, everything relies on a geometric framework. Consider that every atom in your body will be replaced in the next 7 years, yet you are still you. What stays the same is the geometrical structure. You are pure math. The geometry of life determines more than the shapes of things. How we sense the world depends on its structure. A rose is a rose is a rose. When you smell its fragrance, you're not responding to specific atoms like hydrogen, oxygen, and carbon, but to the arrangement of those atoms into molecules. Without that structure, you'd be smelling water and soot. So mathematics can explain the smell of a rose. But what about the habits of rabbits? In 1202, Leonardo Fibonacci found mysterious math in the breeding of rabbits. Start with a single pair of rabbits in January, and you'll have a second pair in February. In March, the first pair will have a third pair, while pair number 2 is still growing up. So in March, there are 3 happy couples. In April, pair number 1 will be added again, and pair number 2 will have its first babies. Now there are 5 pairs. In May, there are 8. In June, 13. From this breeding frenzy comes the Fibonacci sequence. It caught Fibonacci's eye because each number is the sum of the 2 numbers before it. But it's more than a mathematical curiosity. Look how leaves are arranged around the stem of a plant. Starting with the first leaf, count the leaves around the stem until you see a leaf growing exactly above the first one. For this plant, it's Fibonacci number 8. By retracing the cycle of leaf growth, you can see that it takes 3 circles around the stem to reach leaf number 8. The number 3 also comes from the Fibonacci sequence. These numbers of life change for each plant, but they almost always correspond to the Fibonacci sequence. One of nature's most exquisite forms is the simple curved shell of the nautilus. Like so much of nature, the beauty of this shape can also be explained with an equation. If you take a series of squares whose sides correspond to numbers in the Fibonacci sequence, you can construct a logarithmic spiral, a curve that corresponds to the shape of the nautilus shell. This spiral shape curls through nature with mathematical regularity.
I think the reason you see some of these simple mathematical formulas throughout the world is because they're efficient, they're useful. A logarithmic spiral in a seashell, for example, is there perhaps because it's a way of the animal keeping its basic shape while expanding its size. It's compact, it's energy efficient.
So from the sum of x and x plus 1 comes the shapes of our world. An equation is lurking behind much of what we consider beautiful. We're mesmerized by the regularity of shapes, the predictability of patterns. Even as babies, our brains are programmed to notice particular designs. Science has found that patterns can alter the course of brain development and even affect our judgments of beauty.
If you raise animals, for example, in an environment without pattern, their brain structure actually develops differently. If you, for instance, put a guinea pig in a very deprived environment, something about its brain will be different as it grows up. We are used to seeing patterns from infancy, and probably because of that, it helps us determine our concept of beauty.
So why aren't all patterns equally beautiful?
I think there is a way we can define beautiful patterns. They're not too orderly. They're not like a test bar pattern on a TV screen. They're not too random, like white noise on a TV screen that's tuned to a station that doesn't exist. Beauty is somewhere in between the two. It's that balance between order and chaos.
The seemingly chaotic world we inhabit can be interesting, even intriguing. If you look closely, you can see the elements of order that make it beautiful.
Yeah, I think that there are a lot more underlying patterns in nature and in the way the physical world work than we ever realized. And things that couldn't be explained through mathematics weren't explained. And now we're finding that things that we thought were previously random have limits, have patterns, and operate in systems that we can't fully understand.
Clifford Pickover is working with one of nature's newly identified patterns, busy, often beautiful designs called fractals. They're patterns in which the smaller part reflects the whole. If you look at a mountain range from 100 miles away, then from just 1 mile away, the features look the same because its structure repeats on a smaller and smaller scale. Call it a regular irregularity. The mountain range is a fractal pattern.
Fractals are generally objects that show a quality called self-similarity. By self-similarity, I mean you can magnify portions of the structure at different size scales and continue to see detail. For example, take a branching pattern of a tree or a leaf or even blood vessel branching in the human body. You can look at it far away and see a pattern. You can magnify it and see the same pattern repeated smaller and smaller and smaller.
Because fractal patterns include repeating elements, their beauty can be created using mathematics. Pickover creates his fractals by using equations that sometimes mimic natural processes. He uses algorithms, mathematical recipes that tell the computer what to do.
The key to many of these algorithms that simulate natural forms is the idea of repetition or mathematical feedback loops, something occurring over and over again. Usually it's just a simple rule like grow and then branch into two and grow and branch. And with repeated application of these rules with a computer, you can get a very intricate structure.
By simulating natural processes like growth, Pickover creates fractal images that duplicate the beauty of our world. They look more like they came from nature than from software. Maybe that's why they strike a responsive chord in us. Maybe that's why we find a lot of them beautiful. But patterns are more than just pretty designs. Science is finding that they often reveal order hidden in chaos. To understand the connection, look at some chaos you can keep on your desk. This simple machine moves in a totally unpredictable way. There's no computer on Earth powerful enough to say which way the red ball will move next. It seems totally random. But if you attached a pen to the red ball, an odd swirling design would emerge, showing that even disorder can generate patterns. Building is essential to the expression of humanity. In our creations, we strive beyond pure function toward commentary and celebration. When we set out to create, the patterns and mathematics and nature guide us in our designs. It's hard to overlook the parallels between natural and man-made forms. But there is more to our creations than mere imitation. Man has also calculated nature's proportions. Ancient thinkers looked at nature and wondered if they could duplicate the gods' designs. They came up with the golden section, the measurement of the gods. Take a segment and divide it so that the ratio of the smaller segment to the larger segment equals the ratio of the larger segment to the whole. The numerical value of this proportion is 1 to 1.618. If you construct a rectangle based on this measurement, you can see the ratio is roughly 8 to 5 or 5 to 3. The same numbers found in the Fibonacci sequence. The ancients believed these numbers were sacred, and that might have been because the same proportions can be found in nature. For centuries, artists and architects have built these mystical numbers into their structures.
In the times before the modern age, people gave value to the numbers that buildings are made out of. For example, something might be 3 feet wide and 5 feet high. And those numbers had meaning. The number 3 symbolized God in nature, for example. It also symbolized the Holy Trinity. It had a real symbolic meaning. And the number 5 symbolized humanity. And you'd get the two and you'd put them together and you'd have a shape called the golden section.
Many of our greatest structures and works of art subscribe to this proportion. The Parthenon, Notre Dame, even Michelangelo's creation falls within these so-called divine proportions. But few would suggest Michelangelo painted by numbers. He was creating what felt right to him, what he felt was beautiful.
It's built into us to understand the relationships amongst forms, to understand the way patterns relate, and to make shapes that relate to each other, that are harmonious just the way the speech that we make is grammatical and makes sense. And so intuition is going to go for that shape without sitting down and calculating, oh, it's exactly 1 to 1.618.
What of invisible beauty? There are patterns in the air, sound waves that can make our spirits rise. Again we find hidden structure, a mathematics of music that predicts sounds we will like. Legend tells us the Greek philosopher Pythagoras discovered the relationship between numbers and sound while walking by a blacksmith's shop.
He heard some hammers falling of different weights. One hammer was 12 pounds, another was 9, another was 8, another was 6. So he noticed that each hammer made a different sound, and when they were struck together, they harmonized. They formed a certain type of interval. So this is the 12 pound. This is the 6.
Some musical math is as simple as x and 2 times x.
So they're both, 6 and twice 6. They sound basically the same sound, but what we call an octave apart.
The relationship is easier to understand when you use strings. If you take a single stretched string and pluck it, it sounds a note. Notes in harmony with this one come when you divide the string at precise points. If you divide it in 2 parts by pressing on the middle, it sounds an octave. In 3 parts, it sounds the 4th. In 4 parts, it sounds the 5th. A discordant sound results when the division of the string does not come at an exact interval. These simple ratios represent the foundation of our musical scale.
And what this meant was that mathematics had a concrete relationship with the world, that the world worked in a mathematical way, and that simultaneously our own sense, our own aesthetic sense, that makes us recognize harmonies and disharmonies, is a way of perceiving that mathematical relationship in the world. And so there's this wonderful threefold connection between a human mind that can experience this, the mathematics themselves, and the physical world.
By the Middle Ages, architects and composers were linking the mathematics of music and the structures they built. One architectural measurement, the golden section, can be translated into an interval called the major sixth. This is the music of the nautilus shell and breeding rabbits. Different measurements correspond to different sounds. Now, listen to the architecture of Notre Dame.
People would go to the cathedrals, and they had a full-time choir, I think it was 60 people in Notre Dame, singing music made up of the intervals that were the same as the intervals, as the proportions that actually composed the building. The buildings were designed literally to embody musical intervals, the musical tones, the musical intervals, say a third or a fifth or a fourth. Those were ratios that were taken from music and transposed literally into buildings.
The relationship between structures and sounds suggests that mathematics are essential to man's creation of beauty. But numbers cannot explain it all.
Now, there's certain basic principles that are going to remain in there. But with something like beauty, you can't legislate that. Because you don't know what it's going to be.
And that's why beauty is going to be something different for every person.
Keep watching. Discussion topics and activity and resources for patterns, symmetry, and beauty are up next on Assignment Discovery. Now that you've seen patterns, symmetry, and beauty, talk about this. Look for examples of the Fibonacci sequence and the golden section in nature. What are some examples of the Fibonacci sequence and the golden section in your immediate environment? How are these relationships expressed? Now try this. Using straws, tape, and a ruler, construct a model that embodies the golden section. For your measurements, use different sets of numbers greater than 3 from the Fibonacci sequence. Log on to DiscoverySchool.com for curriculum materials and resources to support patterns, symmetry, and beauty. To learn more, Assignment Discovery suggests Life by the Numbers by Keith Devlin.